Okay. Now, let's recall the so-called eigenvalue problem. Right? A is an m by m matrix. Okay, so if ax equals to lambda x, sorry, if lambda is such that, if lambda, which is a scalar, is such that ax equals to lambda x has a non-zero solution, x not equal to 0, then lambda is called an eigenvalue of A. X, such a solution X, is called an eigenvector of A with eigenvalue lambda. Okay, so to find lambda, find eigenvalue, right, we need ax equals to lambda x to have non-zero solution. That is equivalent to say that A minus lambda I has non-zero solution. Which is the same thing as saying that A minus lambda I, this matrix, is singular. Okay, now by the previous long discussion about this determinant, this is the same thing. To say that A minus lambda I is singular is the same thing as saying determinant of A minus lambda I is 0. Okay, so what are we talking about here? So this is therefore the condition for lambda to be an eigenvalue. So condition for lambda to be an eigenvalue. Okay. So lambda is not known, right? Eigenvalues are not known before we solve for them. So therefore, what we're saying is we should formulate the following definition. A is an n by n matrix. The characteristic polynomial of A is this polynomial in T, in the unknown T, that is the determinant of A minus T times the identity matrix. So like I said, T here is unknown. Okay, this is the characteristic polynomial of the matrix A. And the definition is formulated in such a way that lambda, sorry, not lambda, eigenvalues of A are precisely roots of the characteristic polynomial. Right? That's pretty obvious from the discussion we had. Now, the second fact is the following. Right? We're taking the determinant of the matrix A minus Ti, and let's look at this a little bit more carefully. If A is written in the usual form, then A minus Ti is basically the same thing, except for the diagonal entries you have A11 minus T, A22 minus T, and so on. Okay. Okay, so the diagonal entry, only the diagonal entries carry this unknown T, and there are n copies of T occurring. Right? So if you think about computing this determinant, say, along the first row, you're gonna have A11 minus T times some minor, and other things. I mean, and you will have, if you think about it for a minute, you see that you will have a term that's n copies of T multiplied together, and that's the highest possible power of T it can occur. So what I'm saying is that this is a polynomial in T of degree n. For n by n matrix, the characteristic polynomial is a polynomial in the unknown T of degree n. That's what I'm saying here. Okay. So now what do we know? Because the characteristic polynomial has degree n, because the characteristic polynomial has degree n, it has at most n different roots. So, and the roots are exactly the eigenvalues of A. So A has at most n distinct eigenvalues. Okay. Now, the fundamental theorem of algebra fundamental theorem of algebra implies that this determinant, this characteristic polynomial has at least one complex root. So A has at least one complex eigenvalue. Okay. Now, finally, the fundamental theorem of algebra actually says again, fundamental theorem of algebra implies that you can actually factor the characteristic polynomial into the following form: some constant a times t minus r1, t minus r2, up to t minus rn, where r1, rn need not be distinct. Okay. Right, so one way of saying the fundamental theorem of algebra is that this polynomial always has n roots, allowing repetitions. Okay, so now, so like I said, these numbers R1 through Rn, these roots need not be distinct. Now the algebraic multiplicity of a root in this polynomial is the number it's the number of times the factor t minus r occurs in here. Okay. So again, we are allowed to look at characteristic polynomial. We know that the eigenvalues are exactly those roots, the roots of the characteristic polynomials. The polynomial may have distinct, the polynomial have always n roots, but they may not be distinct. The number of repetitions a given root has is called its algebraic multiplicity. Okay. So now I think it's time to do some examples. Say 0 minus 2, 1, 1, 3. Okay. So let's say this is my A, and I want to compute its characteristic polynomial. That's 1 minus t, 1, 1, 0, 3 minus t, 3, minus 2, 1, 1 minus t. So without much thinking, we're just gonna compute it by expanding along the first column. So it's 1, and then the next term is skipped because it's a product with 0. So we only have the next term. 1, 1, 3 minus t, 3. Okay. So now this is 1 minus t, 3 minus t, 1 minus t, minus 3, minus 2 times 3 minus t. Okay, what is this? 1 minus t. This is going to be t squared minus 4t plus 3 minus 3, so that's gone. Minus 2, 3 minus 3 plus t, so t. So now what we're going to do next is to factor this. Okay. So this becomes t squared minus 4t becomes t minus 4 times t. And then we can factor out a t. And then we get 1 minus t, t minus 4 minus 2. And then we can compute. This is negative 4 plus t plus 4t. Is that right? T negative 4 plus 4t minus t squared minus 2. So that's t here minus t squared plus 5t minus 6. And we can further factor this minus t, t minus 2, t minus 3. Yeah. Okay, so yeah. So this implies that the eigenvalues are 0, 2, and 3. Very good. This is the simple case. Let's now look at another example. Okay, which one is this? Let's say A is 3, negative 12, 4, minus 1, 0, minus 2, minus 1, 5, minus 1. Okay, so determinant of A minus Ti is 3 minus T, negative 12, 4, minus 1, negative T, negative 2, minus 1, 5, minus 1 minus T. Again, this doesn't seem to be any easier way to proceed. So we will just compute it. Let's do this along the first row. 3 minus T, minus T, minus 2, 5, minus 1 minus T, minus 1 times minus 12, 4, 5, 1 minus 1 minus T. Okay, slightly messy. Plus minus 1, minus 12, 4, minus T minus 2. Okay, and let's just proceed to compute everything. So this is minus t times minus 1 minus t, so t, 1 plus t, minus negative 10, so plus 10. right? Yes, and then plus, what do we have here? 12 times 1 plus t, right? Minus 20. Then minus 24 minus minus negative 4t, so plus 4t. Okay, and this is gonna look complicated. Well, we have to do it. 3 minus t, t plus t squared plus t plus 10 plus this is 12t plus 12 minus 20, so minus 8 minus 4t minus plus 24. Okay, now multiply out the first term. Get 3t squared plus 3t plus 30 minus t squared, no, minus t cubed minus t squared minus 10t plus 12t minus 8 minus 4t minus 24. So now we can start cleaning this up. Minus t cubed. How many t squared terms are here? Here and there. So that's plus 2t squared. And now for the t term, it's 3t minus 10t, 12t minus 4t. So 15t, 5.1t plus t. And finally, 30 minus 32, negative 2. Okay. So, well, what are we going to do now? This is the characteristic polynomial. We are hoping to find the eigenvalue, so we have to find its roots. For this one, there's an easy way to proceed. Namely, you split the terms like that and factor out the common factors. Then you get, for the first two terms, you get minus t squared times t minus 2. The second term is still t minus 2. So this is minus t squared plus 1, t minus 2. So that is overall minus t minus 1, t plus 1, and t minus 2. So, okay, so now we can read up the roots, hence the eigenvalues. One minus 1, and 2. Okay, so now let's see one more example. So we're gonna do a very nice case. You will see why it is nice. 1 0 0 0 2 3 0 0 1 minus 1 2 0 0 1 1 3. Okay, so for this matrix A, the characteristic polynomial is this expression, is this determinant, 1 minus t 0 0 0 2 3 minus t 0 0 1 minus 1 2 minus t 0 0 1 1 3 minus t. And now the point is that the matrix we are looking at is upper triangular. So the determinant is simply the product of the diagonal entry like that. So this immediately tells us what the roots are, hence what the eigenvalues are. They are 1, 2, and 3. And there's one thing to notice, that the factor 3 minus t occurs twice. So this means that 3 has algebraic multiplicity 2. Other guys has algebraic multiplicity 1. Okay. So now we can try to think about the following question: how to find roots of the characteristic polynomials. Right? We've discussed so far, the discussion have led us to the understanding that if we want to find eigenvalues, we have to find the roots of the characteristic polynomial. But how do we do that? No, so the point is, the polynomial, the characteristic polynomial has degree n, right? If n is 2, we can solve for roots using the quadratic formula. Right? We've never talked about what we do if n is bigger than 2. So say if n is 3, the situation is that if n is 3 or n is 4, there exists formula for methods for finding the roots. Not quite formulas. There exist methods for finding roots. Okay, but unfortunately, if n is bigger than or equal to 5, there isn't an algebraic method for finding roots in general. Okay, the word here is in general. There is no algorithm, recipe, or whatever that produces these roots for any given characteristic polynomial. But if the characteristic polynomial takes some special shape, it is possible sometimes. Okay, so that's what it is, and we're just gonna have to learn to deal with it. Now, there are, however, some other venues that we can pursue. So here comes the theorems. Yes. So the first general property we can make is that A and the transpose of A have the same characteristic polynomial, hence the same eigenvalues with multiplicities. Okay, so this is very easy to see because the characteristic polynomial of transpose of A is this. And because T times the identity matrix is actually diagonal is equal to its own transpose. So you can therefore write this as the determinant of the transpose of A minus Ti. And we've known before in a theorem that says the determinant of A and it's the determinant of a matrix and the determinant of its transpose are equal. So we arrive at determinant of A minus Ti, which is the characteristic polynomial of A. Is that simple? Now, okay, let's move on to the next theorem. A equals, let's suppose A is an n by n matrix as usual. And let's say lambda is an eigenvalue of A. Then first, for every k at least 2, lambda k, the k power of lambda is an eigenvalue of the k power of A. Second, if A is non-singular, or should I say invertible, then lambda is not 0, and lambda inverse is an eigenvalue of A inverse. 3, if alpha is a scalar, then lambda plus alpha is an eigenvalue of A plus alpha I. Okay, and proof. All these can be proved by the defining property of eigenvalues. So say x not equal to 0 is an eigenvector of A with eigenvalue lambda, which just means that Ax equals lambda x. Then now we proceed to proof 1. So if we are looking at the k power of A applied to x, and we're going to use property of matrix multiplication to write it like these, right? The k power of A is the k minus first power of A times A. And then you use associativity of matrix multiplication to do this. Now Ax is lambda x, okay? And that means, and when you have a scalar multiple, you can take it outside. So you get k's power of A applied to x is lambda times k minus first power of A applied to x. But you can do this again. Ak minus 2 Ax lambda Ak minus 2 Ax lambda AK minus 2. Well, AX again, right? So that's lambda X. And once again, when you have a lambda, you can factor it out so that you get lambda squared on the outside and AK minus 2 times X. Okay. So here's what we're gonna do. We keep doing this and splitting off one copy of A at a time and act it on X and use AX equals lambda X. And that will give us lambda cube, AK minus 3X, lambda fourth, AK minus 4X, and so on. Right, so the point to notice is that you get how many, the number of copies of lambda you get is the number of copies of A you lose. Right, so like that. So in the end, you run out of, you used up all K copies of A, and you get lambda to the K's power times X. This is saying that, having a non-zero X, making this happen, is saying that lambda to the K's power is an eigenvalue of A to the K's power. Okay. So now we move on. If A is invertible, then we can do the following. We can multiply the equation by A inverse. Okay. And then that gives, on the left-hand side, we have, what do we have? A inverse A times X, equaling the right-hand side being lambda times A inverse X. Now, A inverse A is the identity matrix, n by n. So you just get lambda here on the right-hand side, A inverse X. Now the identity matrix I times X, that's just X. So X is equal to lambda A inverse X. Right? If lambda were 0, this right-hand side would be 0, but X is assumed to be non-zero, right? We made the assumption that X is non-zero. So lambda is not 0 because X is not 0. Lambda is not 0, and when lambda is not 0, you can divide by lambda. You get 1 minus 1 over lambda times X equals to A inverse X. And this equation is telling you that 1 over lambda is an eigenvalue of A inverse. Okay, simple. Now the third property, so I want to consider A plus alpha I. So I just look at A plus alpha I and let it act on X. That's AX plus alpha IX. So AX is lambda X by choice. I times X is X, so you get alpha X, which is alpha, so lambda plus alpha times X. And this equation just says that lambda plus alpha is an eigenvalue of A plus alpha I. So that's it. Okay. And you can use this statement, right? If you have some A that you know the eigenvalues of, then you can use this to determine these, these eigenvalues of these matrices without actually computing these matrices. Okay. Yes. Right. So next theorem. A is singular if and only if 0 is an eigenvalue. Okay, proof is the definition. More precisely, by definition, A is singular if and only if there exists x non-zero such that AX is 0. And you interpret 0 as the number 0 times x. And this is the same thing then as saying that 0 is an eigenvalue. Okay. So finally, just left with one more theorem. Now if T is an n by n triangular matrix, okay, then eigenvalues can be read immediately. Eigenvalues of T are the diagonal entries. Namely T11, T22, and so on, Tnn. Okay. Proof of this is more or less obvious because, again, to find the eigenvalues, you consider the characteristic polynomial, which in this case is the determinant of this matrix, T11 minus 1, sorry, T11 minus T, T12, T1n, T22 minus T, T2n, Tnn minus T. Say this is upper triangular. In the upper triangular case, the lower triangular case, the argument is similar. The upper triangular case, everything down here is 0. And you know how to compute this determinant by expanding along the first column n times. You'll get T11 minus T, T22 minus T, up to Tnn minus T. From this expression, you immediately read off the roots, which are the eigenvalues, to be this T11, T22, and so on. Okay, so that's it. That's very simple. So now the next thing we're gonna do, now we talked about how to what extent we can and how do we find eigenvalues. The next thing we're gonna do is to study the eigenvectors. Once we found the eigenvalues, we know how to find the eigenvectors. For each eigenvalue, we have some system to solve. We can always try to do that, but then there are some related notions that we should develop, and we'll do that in the next lecture.